All right, I think I'm good to get started. So I just wanted to say a few things about the webinar first. This is the first one we've done. It's going to be called the Beard Tribology Webinar, and I'll explain why. But thank you all for participating. It's something we hope to do every month, at least for 2021. So yeah, I wanted to make sure everybody remembers Ralph Beard. He was, many of you knew him, he helped start the tribology minor at Auburn and was very supportive. He was well known throughout the tribology community. He passed away a few years ago, but because of the work he did with us, he has a fund named after him at Auburn. And also this webinar is named to commemorate Ralph. And hopefully he's somewhere right now watching this and he's happy with what we're doing. So the program, very short. We have two programs right now that you might be interested in. We have a minor that's mostly for undergraduates. So that's kind of unique. We have about 20 students in there at any given moment. And if you want to know information, I put the web link here. You can contact me if you want me to send you the information directly. It's open to all science and engineering students at the university. And then we also created recently a graduate certificate. So the idea with this is someone in industry who doesn't have necessarily an undergraduate degree in mechanical engineering could pursue a certificate in tribology and take some of the courses we offer. So there's a link for that as well. I also want to thank the advisory board. Ross Shaw and Maureen Hunter, who are leading the board, actually proposed the idea for this webinar. So we wouldn't have done this without their suggestions, and they helped line up the speakers too. But everybody else on the board also appreciate their help, and we're in communication quite a bit. Some of these people on the board have been helping us for almost 10 years. So I really appreciate everybody's help and support. And also we have some people who've helped in other ways, donated to scholarships or have awarded scholarships to some of our students. We really appreciate the help. This is not everybody, so there's a more complete list of everybody who supported the minor on our website it's there from everybody supported through the years. So with that, that's all I wanted to say, and I think we're about ready to get started. Might have to switch the slides here, but I'd like to introduce Heidemarie Stephanyshyn-Piper. She's a retired captain of the U.S. Navy. Captain Piper was born and raised in St. Paul, Minnesota. She attended the Massachusetts Institute of Technology on a Navy ROT scholarship and earned a bachelor degree in mechanical engineering in 1984 and a master's degree in 1985. She served in the U.S. Navy for 30 years and retired in July of 2015. As an engineering duty officer, she served at various ship repair facilities on maintenance staffs. She's an experienced Navy diving and salvage officer. She was selected as an astronaut by NASA, and she is a veteran of 2 space flights, STS-115 on the Space Shuttle Atlantis in September 2006, and STS-126 on the Space Shuttle Endeavour on November 2008. She's logged over 27 days and 15 hours in space. She has completed 5 spacewalks, totaling 33 hours and 42 minutes. And she and her husband currently live in Oak Harbor, Washington. I'm very thankful to Heidi for doing this. She did a seminar for SDLE a few years ago, and also another seminar on campus at Auburn. Of course, this year we're not doing many on-campus seminars anymore, but I'm very grateful for doing this, and I hope everybody enjoys their sharing of their experiences. So I'll close my screen sharing. And Heidi, if you're there, I guess you could share your screen now.
Okay, thank you, Rob. And let me get this up.
One more thing before I forget. So I have everybody on mute. There's a lot of people on this webinar. So for questions, what I'll do is if you just write in the chat, I'll try to keep an eye on that. And we'll ask some of them after Heidi's made her presentation. Okay, thank you.
Okay, thank you, Rob. And it's a pleasure to be here and happy to kick off this webinar series. As Rob had mentioned, this is basically the presentation that I gave at the STLE conference back in 2015. So hopefully if you remember that one, I'll say the same thing I said back then. But it's still a pertinent story to tell because, you know, lubrication is a critical component and something that's not quite thought of. And even with my time in space and the time that I had in the Navy doing ship maintenance and ship repair, that, you know, the interactions between two moving parts is always a critical component that fails and leads to some major issues. And here's one of them that we had on the ISS. So what I'm going to talk about is the solar array rotary joint failure. And the picture here, this is the solar rotary joint. The joint is right in here. It's covered with shields that help protect the trundle bearings and keep debris out. And I'll go into what the failure was, the recovery, and then some of the challenges that we had working in the space environment. So first, a little bit more about the SARG. There's one on each side. They're inboard of the solar arrays. And what the joint allows is the solar arrays to rotate 360 degrees so that your solar panels can be constantly tracking the sun as you're going around in orbit so as to maximize your power generations capabilities. And there's the ISS. Again, this was a picture taken from the last shuttle flight as they did the flyby. And the SARG, like I said, is right in here. There's one on each side. So what had happened was after they had launched the starboard SARG in September of 2006, or yeah, 2006, or 2007, excuse me, because 6 is we launched the port SARG. That was the first component. The starboard side, the one on the opposite side, was launched later. And the race ring is supposed to be like here, a nice new race ring. Here's where the gear teeth sit in there. And there are 2 drive mechanisms that rotate the SARG. What they had found, and over time, they realized that this race ring was no longer the nice hardened surface, but there were wear particles, and the trundle bearings actually, in a sense, became magnetized, capturing much of the debris. So the first thing in any kind of repair scenario is to figure out what exactly happened. You know, how did it break? And what they found that there was inadequate lubrication on the roller bearings, combined with excessive forces that led to the degradation of the surface. When they put the starboard SARG into operation, very shortly thereafter, they noticed that the current draw on the drive motors was rapidly increasing, significantly more than on the port side, significantly more than designed. So they locked the SARG so as not to further exacerbate the situation. While they went out, they could send astronauts that were out on spacewalks to go remove the panels and inspect the race ring, and that's when they found the degraded surface. They were able to take samples just using Capt tape to try to capture some of this debris and send those samples on a shuttle mission that was coming back to the ground. They did the analysis, and they did find that the material was primarily the nitrated surface that was the case hardened surface where the bearings sit. So through that and analysis, they also found that the lubrication that they had used was a gold film, because in space applications, you know, going back to when the space station was first conceived and designed through the 80s, there was not a long history to be able to say that greases would actually work in the open space environment. Up to this point, the lubrication of choice in open space was primarily solid lubrications, gold, graphite, and greases had been used, but mostly in closed applications. So they settled on a solid application that they found after putting it into practice with the misalignment that led to the roller bearings tipping rather than lying flat. That all contributed to the failure of the Sarge race ring. So then it was a recovery plan. What were they going to do? And so my mission, STS-126, had been slated to do the repairs from the time that they found the problem to the time that our mission was scheduled was under a year, but they felt, the engineers and felt confident that they could come up with a repair plan, and we had time in our schedule that they could execute this plan, and it ended up becoming the primary focus of our spacewalks. So the first thing we did was remove all the trundle bearings. There's a series of 16 bearings spaced along the race ring. There are also bearings on the drive lock assemblies, which are basically the driving force of the race rings, but it had been decided that since there were not spare DLAs available, that they would just leave those in place. We replaced all the bearings. Big concern was removing the debris and then applying a space compatible grease that could be used, that could help provide the lubricating that was needed on the race ring. So in addition to coming up with a repair plan, they had to develop some tools that we could use, because all of this work had to be done outside the space station. So we had to, you know, obviously be in our spacesuits, which makes any kind of repair efforts more cumbersome. And then the final thing is to train the crew so we could go execute our space repairs. Tools for applying grease. We basically took, we called them grease guns, but they were applicators that were not unlike, you know, what you would buy if you were going to do home repair, caulking repair, but they were developed for space use for the shuttle repair post-Columbia. And so they just modified them, changed the canisters to include the grease rather than the tile repair material, had different nozzles, and then we would go off and do the work. All of our repairs, we were practicing in the neutral buoyancy lab, where we practice all of our spacewalks, doing successive repairs or practices runs in the pools. So I figured I can't talk about shuttle without showing a shuttle repair. or a shuttle launch. So that took us through our first 2 minutes of flight on the solid rocket boosters. And then we continue on the main engines for another 6.5 minutes. So the shuttle's launch was 8.5 minutes from liftoff to orbit. Once we're in orbit, we get rid of the external tank. It's jettisoned, it's no longer needed. The tank provides the fuel for the main engines. And then we're in orbit. And so that takes us through our orbit. So now we're up in orbit. We dock to the space station, and then we go to work. The repair plan, we had 4 EVAs scheduled, and so we had 3 EVAs that were primarily dedicated to doing the repairs on the starboard Sarge. And then a portion of the last EVA was dedicated to also go provide additional lubrication on the starboard, on the port side. Even though there was no indications of failure on the port side, because they had no telemetry that showed anything abnormal on the port side, and from visual inspection, there was no observed damage, but as a precaution, they went ahead and lubricated the port side as well. So this is just a series of clips of us doing the repairs on the starboard Sarge. So once we got out to the work site and we started work, then we would go ahead. First thing we would do is remove the covers to gain access to the race rings. Then we would take out the existing trundle bearings, doing visual inspection of each section that we gained access to, so that the ground had documentation of what we saw, taking pictures as well. So that was the best method that they have of getting an as found condition. Then we would clean up the debris that was still visible. To do that, we had these, they were just wipes that had been impregnated with the grease that we would be using. The grease was a brake coat component that was settled on. And then on, in addition, if we needed more grease for an adherent to collect all the debris, we had the grease guns. And so we would just continue going from one to the next. Once we got everything cleaned up and applied a bead of grease to all 3 surfaces, the trundle bearings, there's actually a component of 3 of them. So we had to put them on all 3 surfaces. One of the surfaces we couldn't see, so they had to design a special hook to get grease on the backside, the internal race ring. We put everything back, and we had special bags so we could bring all the trundle bearings back so that they could use them in further analysis to see if there was any degradation on the bearings. One of the challenges of working outside is that everything you use has to be tethered. Since we had multiple components, using the wipes, the bearings, we had multiple smaller tool bags for use on orbit. So our grease guns on orbit, as I said, these were tools that they modified from a different application, but our grease turned out to be a little bit more troublesome working outside. Even though they had done some tests on a previous shuttle flight that confirmed that yes, we could use this outside, but because we were using it much more, it turns out that the grease liked to free flow. Even though they had installed a shutoff valve, and the thought was that the shutoff valve would prevent any leaking grease. Unfortunately, right beneath this is just a ball valve, and the grease provided a very good lubricant for the ball valve. And the shutoff valve did not take much effort to basically, turn it from a closed position to an open position. And even though we had caps on the end of our grease guns, at the very end of the cap, it was this thermal cover was sewn, and so at the very tip, the grease that would just tended to free flow, because you can see where there's little gas pockets inside. Spending time in the space environment was excellent for those little gas pockets to be enough of a flow to force the grease out of the grease guns. And unfortunately, I was the first one to find this problem when I reached into my tool bag to take out tools, and I got grease on my hands. And that was a concern because they did not want the entire outside of the space station to look like this and be covered with grease. And so that's why we had all of these precautions. Well, it turned out that the grease was more free flowing. And in my, when I saw the problem, okay, first thing, clean everything up. So in my bigger toolbox that I had smaller tool bags and new trundle assemblies and bags of the old trundle assemblies and bags with all of our wipe tools. There's one of my tool bags, because at the very end found out that even though one of our mantras is all of your tools are tethered, it turned out we had missed tethering one bag. And that tool bag actually sat in an open box for about 45 minutes before I came back, disturbed it, picked it up, let it go, and it flew away. Or it didn't float away, it floated away. And that was not the highlight of the flight. But unfortunately, when this happens 2.5 hours into the first of four EVAs for repairs, we had to come up with a different plan. And it turned out, even though we did lose one set of grease guns, we had two. And it just meant that my partner and I had to share tools. And we found out a better way of just doing it and sequencing. We ended up using less grease because we didn't have two complete grease guns. And the end was that we were able to complete all of our repairs, get the work done. And this was the space station upon our docking. And so this is the starboard sarge, this is the starboard sarge, port sarge. Had two arrays. On the starboard side, they hadn't launched the last set of arrays. They wanted to fix the sarge first. So the race ring had been locked in place. So on our docking, that's why the two arrays were different. But even by the end of our mission, they started running the sarge. And by the end of our mission, after we undocked, we undocked about a week after our last EVA, they were confident enough that they operated the Sarge. And so you can see both solar panels being in the proper alignment for our undocking. And what they did find is after they did put it into full operation, looking at the drive current. So here was the, when they started noticing the initial problem on the starboard side. By our mission in, it was November in 2008, we greased the Sarge. They could tell that on the port side, after we just provided as a preventative method grease, and then they started recording on the starboard side, put it back into full operation. It pretty much was at the same level as the port side. And here it is 12 years after our repairs, and the race ring is back in operation. So it did work. And so finally we came back home. So I just thought I'd throw the clip in of our landing. On the space shuttle, the day before landing is when we put all of our equipment back. And on landing morning, we get all the crew members dressed up again in our launch and entry suits. We don't wear them on orbit, but we'll wear them for landing. Coming in, if you notice the map on mission control, they had to keep us in orbit because bad weather in Florida. And so they sent us to Edwards Air Force Base, which is the shuttle's alternate landing site in California. It was a beautiful day there when we came in. The shuttle's landing pattern, we come in, fly around the airfield, line up on final, and come in. At this point, we are just landing like a big glider. We have no engines for our re-entering. After we do our deorbit burn, then it's a matter of just slowing down, coming down in altitude, and arriving at the runway. So our shuttle touchdown much faster than most commercial airplanes, but that's just because of our wingspan and maintaining lift. The parachute helps slow us down once we get onto the runway, because after the initial first shuttle flights did not have a parachute, and they did notice that there was heat buildup on the brakes. And so to assist in slowing down, we added a parachute. But once we slow down, we'll get rid of the parachute, roll out to the end of the runway. And then we can get out of the vehicle, and they refurbish the vehicle again for another flight. Except we're not flying the shuttle anymore, and now we have a new launch capability, and we're still back up servicing the space station. So that's what I had prepared to tell you about our story of lubricating the ISS in space. And
thank you, Heidi. I think if it was a live talk, you hear an applause right now.
Okay.
And just, I've seen the talk before in person, and actually seeing it on a screen, I could see more of the details of like you in space, and it was hard to see on a big screen, for me at least. Anybody else have any questions?
That doesn't look like any questions.
Here's a few.
Okay.
Someone I think it's more of a comment.
Yeah.
They said that the grease should have been serrated to eliminate the air bubbles, so it wouldn't ooze out.
So that might have been a good as a hindsight, and I'm not sure if that is what they do now, because there was, when I left NASA, so I had left NASA in 2008, shortly after the flight. And I know when I had left, there was talk about how often they would have to go and relubricate the race rings. But I have not seen or heard of any EVAs that were dedicated to doing that, maintenance work on the Sarge. So my guess is that they've been comfortable with the repairs that we did and did not find a need to have to go out there. And so I just saw the quick one about who's up for an expedition to look for that grease gun. Interesting enough, after the flight that I guess when I let go of the space of the bag, I did put it in a somewhat retrograde orbit. So its orbit was decreasing, and they were able, not they, but they being, amateur astronomers were able to track the tool bag. And I was told there was even a website put out called Track the Tool Bag. And so they were able to track it for 9 months. And after that, it did deorbit and it just burned up on reentry. So no expeditions needed to go look for the grease gun. Okay. Was it determined why the starboard side failed, but the port one did not, since they were both initially lubricated the same way? That is true. And what they suspect is that the starboard race ring may have had a defect in the surface. So the race ring is a 10-foot diameter steel ring that the 15 thousandths outer level was nitrided to provide a hard casing. And so they think that there might have been a defect in there. And when you had the misalignment of the rolling bearings, that it was enough to start it, to start the failure. And once it started, it just continued on from there. Another thing, what they might have thought is that after we went back and looked at the port ring and started greasing it, is whether or not one of the trundle bearings was leaking, and there was enough lubrication that was provided from there. That was one of the other things that I heard talked about as to why they think the starboard had failed and the port did not.
There was another question earlier about why gold was chosen and not aluminum disulfide.
Yeah, I think because there had been I think gold had been the preferred lubrication in a lot of satellites at the time. And so that's why they chose it. But as crew members, I had not been involved. And actually, the ISS was designed way before I even thought about becoming an astronaut. So I had not gone back that far to find out why they had chosen gold over other solid lubricants, other than the fact that it had been used extensively in many space applications. And the reason they went with a space compatible grease versus one that was not, the reason they had not used a grease initially is because they didn't have a 30-year history to be able to certify the space station. And so a lot of components that went up to the space station is that they wanted to have that history. And at the time, they didn't have anything that could be used. And I just see a question here. What really means a space compatible grease as opposed to an earth grease? I think they're just looking for things that would withstand and wouldn't degrade in a space environment from either the temperature extremes that they see, from off gassing, from any kind of degradation that they get from atomic oxygen, things like that. And what exactly is the definition of space grease? I don't know. I just know that NASA uses that term quite extensively. And yeah, that I see that report there from Chris Delacourt and Tim Kranz, is that a lot of the diagrams that I had in here did come from Chris. So that is if that's the same one that I have, that is a good report on the failure.
I think you already kind of talked about it a little bit, but earlier on, some people asked about condition monitoring of the bearings, and how long does the grease last? Or I kind of wonder, have there been any other problems with this since then? Because that was quite a while ago.
Yeah, like I said, that's it's been over 12 years since we did the repair, and like I said, I am not aware of any issues that they've had with the Sarge mechanism on orbit, and so that would just lead me to believe that that it is operating as can be expected.
Another question was, how big is this? Is this the largest rotating component, and how fast does it rotate?
Yes, it is the largest rotating component on ISS. Like I said, the Sarge race ring is over 10 feet in diameter. And so that is by far the largest component, rotating piece of component on ISS. How fast does it rotate? Well, it's designed to track the sun, so it will do one revolution every orbit, so that's about an hour and a half. So I'm not sure what that comes out to be for an angular velocity.
Fairly slow though, yeah.
Yeah, it is a fairly slow moving pass. It's not spinning at multiple revolutions per second or minute. I'll answer the easy one. How far is ISS from Earth? The orbit is give or take 200 nautical miles. And the reason I say give or take is because the orbit does decay. There still is, you still have the effects of gravity from Earth, and you also have, there is some drag from the size of the space station. So they do periodically have to do reboosts. And to reboost the space station, they've used a number of methods. Sometimes when a Soyuz rocket was attached, they would use the Soyuz to help assist the boost. The space station also has, on the Russian segment, does have rockets that can be used to help to reboost it. And typically a reboost will only be, on the order of, just a few nautical miles, 1 to 2 nautical miles at a time.
Someone asked how much grease was used.
Oh, good question. I am not sure exactly how much we ended up using. I know we ended up using significantly less than they had projected, and they gave us a big problem. I do see a question, any concerns about overgreasing in this procedure? Well, the biggest concern they had with overgreasing was that they would get grease contamination on other components on the outside of the space station. They definitely did not want to get any grease on the outside of the space station, because if you look on the space station, most of it's that's covered with with multi-layered shields, and that's there as a deterrent against micrometeorite hits. But it was not a concern that it would lessen the fabric, but they were more concerned about getting isolated hotspots in the fabric, and then getting grease contamination and other components on the outside of the space station. So that was their biggest concern with the use of the grease.
There's a couple of questions I think we can more people are asking about condition maintenance. And someone, actually Hannah, who is a tribology minor student who works for a space technology company now, she asked, are all astronauts taught preventative maintenance techniques?
So as part of our training, yes, we are taught preventative maintenance techniques for whatever vehicle we're flying on. So for me, it was primarily on the shuttle, and my work on the space station was there as a shuttle crew member. My first flight, we brought up the port sarge, and so on my second flight, we did the maintenance on the starboard sarge. So we are trained prior to flight for what we're going to be doing on the mission, and whatever preventive maintenance tasks would be scheduled during our flight. And then as far as other maintenance tasks, we are trained on likely maintenance tasks, but what usually seems to happen is things will fail that weren't anticipated to fail. And so then it comes down to that the procedures would be developed, and if it's something that the ground feels that the crew members on orbit can execute those activities without having prior training on the ground, then they'll go ahead and do that. And then otherwise they'll just wait until the next flight, and then they'll train that crew for whatever procedures need to be executed on orbit.
Are you okay for more questions, or?
Sure. Let's see. There was a question in there. Sorry, I see one about the unclassified documentation on the composition of space grease. If there is any information proprietary, some of that does come from the manufacturers. And actually, I was trying to look up. So the type of grease that we used was Braycoat 603, and I tried to look that up, and I couldn't find anything online. So, and I don't know if it's just it's 10 years later, and so that formulation is no longer in service, and so I think most of it, anything that would come out, something like that, NASA really doesn't have proprietary information. If it is, would be from a vendor. And just like any other, trying to get the chemical composition of any other, material that you use.
Let's see. Someone asked about who's handling tribology at NASA right now. I think there's a lot of engineers who are involved in different things. So
there are a lot of engineers involved with it. I know that Chris Delacourt was a big lead in a lot of the tribology work that NASA was doing. And I'm not sure if he is still, I've lost contact with him over the years, and I'm not sure if he is still, he's still there? Okay.
As far as I know.
So he would be.
Good, sorry.
No, I was just, he would be a good point of contact about any current issues that that NASA would be working on.
They're asking again how what requirements are different in a space application than, say, an automobile application.
Well, the biggest thing is that you're working in you're in a vacuum, because space is a vacuum, so that has its challenges. You have the temperature ranges in space, so from day pass, night pass, the heating from the sun, and then when you're on the backside of the Earth, you have nothing, and so you do get the huge temperature changes on orbit. And then the other one that they're very much concerned about is any kind of degradation from atomic oxygen does tend to lead to issues on orbit. And those are all things that you don't get in an automobile application. But then in an automobile application, you have other challenges. You have more debris than you're going to get in space. and also you're working at higher rotation speeds.
Some of these other questions are kind of similar to previous questions about the lifetime of the grease. Trying to figure out where the grease came from and who manufactured it.
Well, I think brake coat is manufactured by Castor Oil.
Okay. So I'm sure people are going to be looking up, trying to
Yeah, I
find
bet
this.
you they are.
Are there any other non-solid lubricants used on the International Space Station?
There probably are, but I just off the top of my head, I don't know where they used, you know, which lubricant they used in which process or which component.
I'm going to open this up to audio now to everybody. See if I can do that. If there's any other questions, so we have one more question. Or how are condition maintenance practices scheduled and prioritized for monitoring in the space station? I think we kind of discussed that before. Might not be anything else to say about that.
Yeah. So maintenance. You know, so we do have, you know, certain preventive maintenance tasks scheduled, and it's, you know, based on like any other component you would have.
Oh, sorry, I just muted you.
Okay, I think
Okay.
I unmuted myself.
Yeah.
Yeah. So every component does get launched with a maintenance schedule for it, and so you know, just like anything else, like whether it's your, you know, your car or your house, or, you know, like when I was in the Navy on ships, you know, they have a preventive maintenance schedule, and then you know, the shift had gone then to condition maintenance as opposed to time maintenance, so that because on space station you can't really you know, you can't send things back for repair. You either have to have a replacement component on orbit or be able to, you know, do, you know, whether it's, you know, preventive maintenance can be anything from, you know, cleaning filters to, you know, replacing filters, replacing components on a routine basis. And so for all of space station is they have a maintenance schedule, and a big part of what the crew members do on ISS is maintenance.
Have you heard anything about Krytox, DuPont product being used?
No, I haven't.
So if you have any more questions, I've unmuted everybody, and also I did that. So if you want to give Heidi a round of applause for thank you for doing this, I think she'd appreciate that.
Thank you.
You should present that to, I think, a request for a younger audience, and a lot of the STEM programs would be fantastic.
Yeah, I do present a lot to a younger audience. I usually don't go into this much detail on the Sarge for a younger audience, but I do talk to students quite a bit to get them interested in STEM and to keep the focus. And, you know, I've gone out and talked to, you know, I've talked to elementary school, middle school, high school, college students, and it's interesting when you talk to those different groups is that it seems like everybody in the elementary school loves math and science and loves STEM. You get to middle school, yeah, most of them will still like math, but that's what I think where you start losing some of them. And it's interesting, in high school, it seems like a lot of them have already made up their minds of what they think of math and science and a STEM career. A lot of them that are still very much interested in STEM as a high schooler, I'm really surprised to see a number of them that go off to college and they realize, they get to college and find out, you know what, engineering's hard. You know, just getting through calculus and differential equations is hard. And so I tell them, yeah, it's hard, but it's not impossible. And you just got to stick with it and keep at it. And that's the only way you're going to get through it. And once you get past the basic grind of calculus and you get into the more interesting parts of engineering and you get into a lot of the hands-on, then it becomes actually much easier. So we just got to get out there and keep the kids interested. And one of the things is, you know, you go out there and talk about space, and everybody loves space and loves to hear about what you can do in space. And I like a presentation that Chris Delacourt gave that he shared with me. Is he was talking about space and talking about all the neat things that he has done with NASA. And you know, one of his points is, hey, you don't have to be an engineer or you don't have to be an astronaut to do cool things in space. And that's one of the other things that I always tell the kids too, is that, hey, if you want to be an astronaut, that's great. But you have to be something else first. And I strongly recommend engineering because I think you can do a lot with it. But you have to make sure that you have a career path and you have something that you really, really enjoy doing, because so few people get to be an astronaut. Right now, NASA's going through a selection process that's kind of been put on hold a little bit because of COVID, but they got 12,000 applications and they'll probably pick about 12. So the odds are very, very small, which is why you better make sure that whatever career choice you picked is something you like to do, because you're more likely to end up doing that throughout your life than becoming an astronaut. But just because you don't fly in space doesn't mean you can't do neat things.
I think that's kind of similar to a lot of the issues we deal with in engineering and tribology. A lot of students come in, or a lot of people kind of fall into tribology because a lot of people don't know what it is. It's not discussed much. And somebody might think, I'm going to go design, you know, race cars or something, and then, or airplanes or spacecraft, and maybe they do, but then later on they find out about tribology and the importance of it.
Yeah.
I guess we're about done. Any other last minute questions?
I have a comment on this. Is Hitesh Trivedi. Can you hear me?
Yeah.
Yeah.
I have a comment in response to the Crytox. The Crytox has two inherent problems. One is very high viscosity, and other thing is it attacks the decomposition products, attacks all metals. So basically it corrodes everything at high temperature. Even it does at cryogenic temperature. That's why Crytox is not considered. Second comment I have, did NASA consider different material or deeper case depth for this bearing material so it has better wear debris resistance?
I'm gonna say that I think in hindsight they probably did, but when they, you know, I have not gone into all of the design decisions that went into the design of the Sarge, and so I'm gonna guess that the design that they put forward and that they manufactured was what they thought was adequate. And yes, in 2020 hindsight, they could have probably gone back and looked at a number of different issues and made changes. But at the time, this was the design that was decided upon and what they built.
Okay, thank you.
Yeah, I think we can wrap it up. Do you have anything else
Yep.
you'd like to say?
Nope, I appreciate it. I hope folks found